Okay, we're getting close to the end. Section 5.4, Fundamental Theorem of Calculus. Fundamental Theorem of Calculus comes to us in two parts. Now, if you are Googling videos and whatnot to help you understand things better, if you don't think that my videos are helping you enough and you're Googling other videos, you should be aware that different textbooks and different teachers sometimes permute the two parts. Here's part one. Some textbooks call this part two. Not a big deal, but just wanted you to be aware of that. If you Google some things, some textbooks call this part two. That doesn't really matter. So now what part one says, if y equal f of x is continuous on a closed interval ab, then capital F of x, which is going to equal the integral from a to x of f of t dt, is continuous on a closed interval ab and differentiable on the open interval ab, and its derivative is little f of x. Okay, so that's what it says. Now, in symbols here, what it says. Capital F of x is this integral right here. Capital F of x is the integral from a to x of f of t dt. And so what the fundamental theorem of calculus is saying is if you take the derivative of that, if you take the derivative of capital F prime x, all right, you've got a little derivative symbol there. You can just barely see it, but it's there. We'll zoom in just a little bit. Well, I didn't need to zoom in that much, now did I? So you can really tell that I am not a professional videographer. There, that's pretty good. So you can see the little derivative symbol there. If you take the derivative of capital F prime of x, where capital F prime of x is that, so then just different notation. Now, instead of having the f prime, I'm going to do dy dx, so derivative symbol, and then this is what capital F is. Capital F is that integral. What the fundamental theorem of calculus says is you get f of x, you get the integrand in terms of x because I'm taking the derivative with respect to x, so my answer ends up in terms of x. And this is just confirming something that you actually already knew about indefinite integrals. Remember, indefinite integrals do not have these limits of integration. And we learned when we were studying indefinite integrals, which could also be called antiderivatives, that indefinite integrals and derivatives were opposites, that differentiation that resulted in an indefinite integral, I just said the wrong thing, integration, which let's just start again. Indefinite integrals without the limits of integration, which can also be called antiderivatives, and derivatives were opposites. That if you differentiated your antiderivative, or if you differentiated your indefinite integral, those things would undo each other. That differentiation and indefinite integrals were opposites. Well, we have a similar thing going on here. The derivative of this definite integral. The derivative of this definite integral, they seem to undo each other, getting me back to f of x. So it really is just confirming something that we already knew about definite integrals, that the derivative and an indefinite integral, those were opposite operations. Now, we aren't going to do a whole lot with this particular part. Part two for our work is way more what we want to work with, but just doing a couple quick examples here. So find dy dx for each of the following. So I just want to take the derivative of y. So dy dx is going to be the derivative of that integral. Integral from 1 to x of 1 over t dt. And I didn't really need the parentheses there. I just put the parentheses there because I like them. So this is a direct statement of the fundamental theorem of calculus part 1, that if you were differentiating an integral where you have a constant as the lower limit and x, and you're taking the derivative with respect to x as the upper limit, the fundamental theorem of calculus is saying that that derivative and integral, quote unquote, cancel, undo each other, whatever you want to say, and you get back to that integrand, just 1 over x, with respect to x, because it's the derivative with respect to x. Now doing a similar thing on the next one. So I'm going to take the derivative of that integral. Now this doesn't have the perfect format. If we go back up here and look at what it says, I need that constant at the bottom. That needs to be the lower limit. That's not what I got here. So I need that 2 at the bottom. Well, I can achieve that by merely interchanging the limits as long as I negate the integral. Does that work for me? So there's my I'd interchange the limit. Really? Neither one of these want to work? There we go. Interchange the limit as long as I negate the integral. And then that negative sign can come all the way out to the front. And so I have the derivative of the integral of sine t dt. And now it is a direct application of the fundamental theorem of calculus, part 1. And that's just going to give me negative sine x. And there's that guy. So there's the fundamental theorem of calculus, part 1. And we could go into much more detail where you have to pick and choose the things you can get done in a semester. So that's where we're going with that one. Now working to the way more important part of the fundamental theorem of calculus, at least in my opinion. So starting towards that. Okay, so this guy right here is an indefinite integral. No limits of integration. And we evaluate indefinite integrals by finding the antiderivative. So the integral of 2x squared plus 1 dx is 2/3 x cubed plus x plus c. The answers to indefinite integrals are functions. Remember the plus c there, the constant of integration. The idea there was that any particular function has infinitely many antiderivatives. So to account with the infinitely many antiderivatives, we put the plus c there. And then remember, you can always check your indefinite integrals. You can always check your antiderivatives by just differentiation. So when I differentiate my answer, I get back to the original integrand. Indefinite integrals, that's what we did in 4.8 and 5.5, use substitution. Went out of order a little bit there. Now contrast that to the definite integral, 0 to 3 of 2x squared plus 1. The answer here is a number. And in the last section, we calculated that using the limit of a Riemann sum. And we did it for 20, and we got 21. So remember what the Riemann sum thing was. That was drawing all those rectangles and then envisioning that as those rectangles got smaller and smaller and smaller, taking the limit as n goes to infinity of all those rectangles and adding up the areas where, not necessarily area because it could be negative, but we'll use the word area anyway, adding up the areas of all those rectangles. And when we did that with all that algebra, we got a number for an answer and we got 21. But for our purposes right now, for the next 2 minutes or so, the way we did a definite integral was to do a limit of a Riemann sum. Officially, it was the limit as the norm of the partition P went to 0 of the summation from k equal 1 to n of f of c sub k delta x sub k, I think are all the right. I think I said everything right there, but if I didn't, not a big deal. The point here is right now, definite integrals were hard. They were limits of Riemann sums. Probably most of us didn't enjoy that too much. But because the notations are so similar, indefinite integral, no limits, definite integral, limits, my God, they look almost identical. There should be some relationship to the way we do them. This guy was easy. This guy was hard. We'd like them both to be easy when they can be easy. Now, not everything in life can be easy, but if this is easy, it seems like that should be easy. That there should be some sort of relationship between that guy and that guy. And there is. Fundamental Theorem of Calculus, Part 2. If y equal f of x, little f of x, is continuous at every point on a closed interval ab, and capital F of x is any antiderivative of little f of x on a closed interval ab, then the integral from a to b of little f of x dx equals capital F of b minus capital F of a. And so there I have just related indefinite integrals and definite integrals. And you're sitting there like, nah, you didn't do that. I would understand that. But I did. It's just the math speak here. Remember what capital F of x is. F of x is any antiderivative. So what this is saying right here, that the integral of a to b a little f of x dx equals capital B minus capital F of b minus capital F of a, it is saying this: to evaluate definite integrals, find the antiderivative in the normal way, where normal's just in quotation marks, whether you need to do use substitution, a power rule, that sort of thing. Just find the antiderivative in the same way that we did back in section 4.8, back in section 5.4, I believe, then, or 5.5, then substitute in the upper limit and lower limit and subtract. So you find the antiderivative just like you would normally, and then you're going to do some arithmetic on the end. You're going to plug in the upper limit, you're going to plug in the lower limit, and you're going to subtract those two values. A little bit of notation here. You're going to see this a lot where they write capital F of x and then a vertical line b to a. What this means is the antiderivative f of x evaluated from a to b, and then what this notation is telling you to do, it's telling you to plug in the upper limit, plug in the lower limit, and subtract. So let's just practice. So we already know that the answer to this one should be 21. Let's get it the easy way. So I start by finding the antiderivative. Increase the exponent by 1, multiply by the reciprocal of the new exponent. The antiderivative of x of 1 is x. And now evaluated from 0 to 3. Notice no plus c. There is not a plus c because these are definite integrals. And in a definite integral, the answer is going to be a number, so I don't need the plus c. Now this part right here, it should check by differentiation. Now you don't have to show me the checking, but if on these simpler ones, if you can just look at it and say, yep, if I take the derivative of that, I got 2x squared plus 1, you know you're on the right track. So this is saying 2/3 x cubed plus x evaluated from 0 to 3, and now I do the evaluation. I plug in the upper limit, I plug in the lower limit, and I subtract. Plug in upper limit, plug in lower limit, and then I'm going to subtract. Careful use of parentheses. Now it wouldn't matter here because this number is 0. But if this was some other number besides 0 and you didn't put the parentheses there, it would matter. And just be careful with the parentheses. We need them. But now I just do the evaluation. So that's 2/3 times 27 plus 3 minus 0. That is the 3 and the 27. Cancel, leaving 9. And so that's 18 plus 3, 21, which is the exact answer that we got before when we did it the other day with a Riemann sum. We got 21, and we're getting 21 today. And there's my first example using the fundamental theorem of calculus part 2. And that's the way you want to do your definite integrals unless instructed otherwise. If I tell you, use the limiting procedure, use a Riemann sum, well then you need to use a Riemann sum or the limiting procedure. But if I don't tell you, you use the fundamental theorem of calculus. And that's where we will end this first video, and we will just practice more on the next video.